last talk for today, Rajesh Mondal, talking about applying neural networks to epoch of reionization.
Hi everyone. So I shall talk about this constraining reionization history and model parameter using machine learning. So this is a MSc project of Sarlo, and we are just started doing this. So I will not present much result, but I'll briefly summarize the previous works and the motivation behind our this project. So since no one has talked about this epoch of reionization, so let me first introduce the subject. So the epoch of reionization is when the universe was reionized again. Means initially the electron proton are recombined here, and it's decoupled from the cosmic microwave background, and we have this neutral universe. And these subsequent stages until the formation of first sources is called the dark ages, and the sources ionize the UV luminosity from these sources ionize the universe, and we are basically interested in this epoch. So how do you probe this epoch? So the most abundant element of the universe is neutral hydrogen, or hydrogen, and we use the 21 centimeter radiation, which arises due to the hyperfine transition in the 1s ground state of this neutral hydrogen, and this is a spin flip transition. And when this electron proton are in parallel, this is the higher energy state. When this antiparallel is the lower energy state, and this transition gives rise to this radiation, and the frequency is 1420. And if we are observing further away, so the redshift comes into the picture, and the radiation wavelength is 21 centimeter. So this is believed to be the most promising probe of the epoch of reionization. So what do we see? We see, so unlike CMB, we can observe the epoch in 3 dimensions. That means not only in the sky plane, we can observe it as a function of the frequency. So we can generate a 3D map of the universe using this radiation, and this so we use the radiation in terms of this brightness temperature fluctuation. so as a function of this theta and nu. Fine, but this is, so direct observation is far from reality due to these foregrounds. Foregrounds are like the point source, radio galaxies, and the second one is the galactic synchrotron radiation. So these are almost 4 to 5 order of magnitude higher than the signal itself. So so removing this foreground is the biggest challenge. So what we do, we use use statistical techniques. So we, instead of direct imaging the sky, we statistically detect the signal. So we use the power spectrum, which is the Fourier conjugate of the 2-point correlation function in the Fourier space. So what is it? So we just Fourier decompose the signal. So this is directly, so the Fourier modes are directly correlate, means one-to-one correspondence with the visibility. So in the radio frequency radio telescope. So we just multiply this amplitude and get the power spectrum. So by doing this, we can increase the signal to noise. So we can observe the signal. So the radio telescope, which are currently operating like SK, LOFAR, and other like MWA, are trying to measure this power spectrum. So this will look like this. So this is the theoretical prediction. So this is at various redshift as a function of the wave number. So that's what is being observed by the radio telescopes. And now the main question is, what can we learn from this observation? So the main motivation behind our work is to extract the underlying astrophysical processes involved in this reionization. So that is the main question. So before that, we need to model the reionization. Means we need to have a model of the process, and then we can establish a tool to derive the constant or derive the astrophysical parameters out of this measured power spectrum. Fine. And so for this, we are working on this method for constraining this parameter using machine learning, and it's called the artificial neural network. So there has been many work, but for I'll just briefly summarize the key points of these papers, which is very relevant for our project. So this work started by this Hayato and Benoit in 2017. It's early 2017. So first I'll briefly summarize this paper. Then I'll go into our results. Okay. Fine. So what they have used, first they have used this artificial neural network with just one hidden layer, and use just I think let me recollect 14 input neurons, and there are 3 parameters in the output layer. Okay, and they have used the model of, so the semi-numerical model which they have used is the 21 centimeter fast to generate the power spectrum. So they use to constrain the parameters like this ionizing efficiency, that is zeta, and minimum halo mass, which can be calculated from the virial temperature of the halo, and the mean free path of the ionizing photons. And these are their best conclusion. So they can reproduce the parameters with as low as 70 training sets. So this is combining in their result at three different redshift, and which is very important because these models are semi-numerical, which is not the best model, not the best or accurate model. So there are models like the full radiative transfer simulation, which can give us the best picture of the reionization. So, but the problem is these radiative transfer simulation is very expensive. So we cannot run the tens of thousands of simulation with the radiative transfer code. But they said that the as low as 70 training set can reproduce the parameters. So and they have drawn a comparison between the MCMC technique and said that this is very fast compared to this kind of technique. Next, this is also a similar paper, but they have also used this 21 centimeter fast, but instead of using this just this UR parameter, they have extended their approach to cosmological parameters as well as the X-ray spectral parameters. So, and they have used the HERA experiment to constrain the to generate the mock observation and produce the. So these are their results. So they produce very confined parameter estimation using HERA. That means HERA can. So their conclusion is HERA can, and if HERA measure the 21 centimeter power spectrum, they can produce unbiased, localized parameter estimation. And as I said earlier, this is very quick and inexpensive to compare to the MCMC. And they have also compared their method with the MCMC, and their result is excellent agreement with the MCMC. And the main thing to be noticed is that this technique are very the main pros are this: it can it can get any changes, and you can rerun this chain with means within a minute or so. So that is the main benefit. And then this work is by Smith and Pichard. So they extended their work and used this multi-layer perception with 2 hidden layers, and use the same model, 21 centimeter first. But the main point they have included in their work is to means like not only they constrain the parameter, they can take the so they have not only they have included the power spectrum, they use the K mode and the redshift as the input. So that is their extra addition, and the conclusion remains same. So they can predict with training set as low as 100, and which is the scope, as I said, which is within the scope of full numerical radiative transfer simulation. Fine. And finally, again, so this is the same thing, and they have compared with the brute force MCMC simulation, and their technique is in good agreement with the MCMC, and their speed is 3 order of magnitude higher than the MCMC simulation. And finally, so this work compared the 5 different machine learning technique using a different approach. This is the sim-fast simulation, and this is also another semi-numerical simulation, but there are some differences between these two, and they have used these 5 machine learning technique and compared them, and for training they have used 1000 training set, and for validation they have used 500, and for testing they have used the rest of 500 simulation. So what they have found that the best the multi-layer perception with 3 hidden layers is the best technique, and which is which can reproduce the power spectrum which 10 to the power 8 times faster than the simulation with 4% mean square error. And and they have also did their analysis at different redshift and trying to find out which how they behave. So they found that the higher redshift behaves well, and if you lower the redshift, it is worse for the lower redshift, and that's all for the previous work. There could be more, but I'll just briefly tell you what is the problem and what people are doing to solve this problem. Now, what we are doing in Sussex, so we are using another different model, first proposed by Visual and modified by Anastasia, and we are using this model to generate the reionization map and in turn the power spectrum. And our model parameters are the first one is the star formation efficiency and the minimum halo mass, which is related to the circular velocity of the halo, and X-ray efficiency, and the final the CMB optical depth tau. So we use these 4 parameters, but we are still trying to find out which sets of parameter is best for us, and for the training purpose we use this 7657, and for testing we used 1915 power spectrum, and our neural network is like like the previous papers, we find that three hidden layer perception is the best for our purpose, and it is better than 20% better than the one hidden layer, and we use this structure of number of neuron in the networks. And finally, I'll present the result, which these are very preliminary result, but still we are getting in close to this what we want to achieve. So the first, this is at a single redshift 14.1, and these are the 4 parameter which I just talked about, and this is the expected value, and this is what we are getting from the network, and this is at a single redshift. But if we include the more number of information, that means if we include information at 3 different redshift, you can see the transition. It means we are getting the accuracy getting better and better, and this is combining 7 redshift. You can see. So if I place it side by side, you can see the differences. What we can tell right now is that the optical depth is insensitive to the network, means we cannot achieve good fit to the optical depth, and there is a transition in this minimum halo mass, which could be because of the transition due to the atomically cooling halo. That means it gives the transition between the mini halo and the massive halo, and that is all, and I would like to say thank you. Any questions? Yeah.
Thank you for an excellent talk. I was just thinking about when you designed your network, you mentioned the increased performance by adding more hidden layers. And for instance, you said you had a number of neurons of 120, 180, 60. Mm-hmm. And I'm designing networks myself at the moment, and it seems to me the guidelines on how you choose those numbers are extremely vague, and essentially we're just kind of clutching at straws. And when we're designing our networks, I wondered whether you had any thoughts on how you actually go about designing the size, the numbers, etc.
So there are 2 things. One, when we don't overfit the data. That is we need to keep in mind. That means when we are training the set, we check the error we're getting after each step, right? So by increasing the number of neuron in the hidden layer, we check the mean square error. And when we are getting, means there is a sweet spot, means like we cannot achieve more accurate result by adding more number of layers. So that is the point we just stop and say this is the best. Yeah.
So you think sort of start with the simplest possible and just keep building until you hit the maximum.
Yeah. The optimal point means the
Any other questions?
I have a question about building the emulators. So we found in a different problem, not reionization, that by using Bayesian optimization to update the training set in an intelligent way, where you balance the current emulator error with the maximum of the posterior, for example, in your current iteration, you can use significantly fewer simulations to achieve the same accuracy of the emulator. Some of the numbers of simulations needed for these emulators that were just described seem to be very excessively high to me. So have you tried that sort of approach? I would recommend it because you could
Yes.
probably cut down quite a lot.